C'est parti.
Okay, today we are happy to welcome Sana Louhichi from University of Grenoble, France. She's a specialist in non-parametric statistics, branching processes, functional convergence of stochastic processes, and long-range dependence phenomena. She graduated from University of Paris 6 in 1998 under the supervision of Paul Duhan. She's a co-writer of a book on weak dependence, weak dependence. It's a Springer book. She has almost 60 publications and at least one known PhD student. I have to say that I know Sana Louhichi since the last century. And I'm very happy to meet her each time in a conference or in a webinar like this. So the title of the talk today of our talk is on bandwidth selection problems in non-parametric trend estimation and the stationary martingale difference of errors with applications to stochastic volatility error processes. Okay, it's done, and I pass it's up to you, Sana. I'm sorry, you're a very humble and discreet person. I didn't find so much information on you on internet. Please put some share your information.
Thank you very much, Wissem. I'd like also to thank Sinabil for this nice idea of organizing this international seminar. My talk will be in connection with machine learning, mainly supervised learning and non-parametric statistics. I try to be not a lot technical, but if we are interested by calculation, we can take a look to our papers with Karim Benhani and Didier Girard from University of Grenoble, Alpes and CNRS. So we have some data. We suppose that the data are of the form xi while I. That means that to each individual, we observe, to each individual I, we observe the input xi and the input while I. And the purpose is to construct using those data a learning function, that is a function from the space of inputs to the space of outputs. This is mainly for two reasons. The first reason is to explain the relationship between x and y. And the second reason is to predict. That means that if you have a given input and we don't, how we can predict its output y. There is a lot of applications of this problem. I will give some real data. Sorry, I have. Wait. I give some real data. They are available in the software R. Here are data heaters. So we have 322 players, and to each player we look at 20 variables. We are interested by explaining the variable salary, knowing the 19 other variables which are in connection with the players, like its age, its experience, and so on. Another examples of real data, they are data from diabetes data. We can find them also in the software, in the library of software R. So we have to explain this disease by observing 10 variables. By observing 10 variables. So we have, as I said, we have to explain the relationship between x and y. So we can write the regression function. We define the regression function as the expectation of y known x. So this is a conditional expectation. And we look at the difference between y and f of x. So while is the true output, while is the true output associated to the input x, f of x is the output obtained by the function, the learning function f. So this is an error, because this is an error between the observed output and the output according to the function f. So if the difference is an error, so we have the model y equals to f of x plus epsilon, and the expectation of epsilon known s equals to 0 almost surely. And the purpose is then to estimate f using the observations. Now, if we know the shape of f, for example, here we are in the case of f is an hyperplane, so we have only to estimate its coefficient. And there is a lot of manner to estimate this. So in the graph, the red points are the observations, and we have to estimate its parameters. One method is to use a least square method, which controls the norm of the error, the distance from the point to this hyperplane, or there's also other method like Ridge lasso method and so on. I give here a nice reference, the book of Asti and his collaborators. Now, when f is unknown, when we don't know the shape of f is always unknown, but when we don't know the shape of f, we are in the case of non-parametric regression. So there's a lot of manner to estimate f using the data. I focus in this talk in kernel method, more precisely the Nadaria-Watson kernel method. So it's given in this definition. So it's the sum of weighted quantity that depends on xi times yi. So it's linear estimators. So this, I will speak, I will give some comments on this definition. So this definition is very intuitive. In fact, the function f that we'd like to estimate is conditional expectation. Is a conditional expectation. So remember that f of x, I tried to write, I'm sorry, I have a problem with my f of, I try to use the pen.
We don't see anything, Sana.
We don't see anything, just a moment. Please, do you see? It's not so.
Okay, there is a blue line now. We see a blue line.
So I can't. I don't know why, but I try to explain it without writing. So the expectation is we have a conditional. I'm sorry, I have still a problem. I'm sorry. I think that I will change the. I'm sorry. I have a problem with my pen. Is it possible to change the? I'd like to change the slide if it's possible, please.
Yeah. Yes.
Yes. So I will change the yes. Partager. So, do you see something here? Is it better?
Yes.
Yes, but I will not use the plane. I have a problem with my. So I said that this estimator is very intuitive. because the function f is an expectation of y known x, and we know that an expectation is estimated by an empirical average. And when we have a conditional expectation, so we will estimate f by the conditional expectation of the outputs when their inputs are around x. So to describe what does mean around x, that means that we are in a neighborhood of x. So we will take a neighborhood of x, we will look at all observation, all the inputs which are in x, and we take the average of all their corresponding outputs. So for this reason, we will have the sum of xi when x is near the observation, the inputs x. So how to quantify the notion of neighborhood? To quantify this notion, we will take a parameter that is h, and we suppose that the observation xi are in a neighborhood of length h. So this estimator uses two quantities, uses the kernel k and the bandwidth h. So when the density of the observation x is known, this quantity up to some constant is an estimator of the variables x. So when the density is known, we will use the true density. So the estimator becomes this formula. Now, as we know that an estimator must be observable using data. So we must, the xi while I are known data, that we observe those data. So we must fix k and h. And the question that we ask, how we can fix the kernel k and the bandwidth h. Now, it's proven that the choice of the kernel k is not too important. But the choice of the bandwidth h is very important. In fact, it affects the quality of estimation. In fact, if we take k as the rectangular kernel is the kernel which is constant on the interval -1 + 1 and equals to 0 otherwise. So it's compactly supported. So if we choose h very small, we can see that using the fact that k is compactly supported, we can see that the estimators equals to 0 for any x which is different from the inputs, and at each values of the input, the estimators equals to the output while I. So we are in the case where the curve of the estimators is very, very irregular. It's 0 while I, 0 while I, and so on. So we are in the case of under-smoothing, and in this case, we have the stochastic error of the estimator, which is the variance is very big. Now, if we take h very big, we can say very big, that means that the neighborhood of x is very big. So all the inputs are around x. So the estimators equals the empirical mean of y. So in this case, the bias is very big, and we are in the case of over-smoothing. I will give some illustration. So in the first case, the bandwidth h is very, very small. So for this reason, the curve is very irregular, the variance is very big. So we are in the case of under-smoothing. We increase h. So here until this value. So here h is very big. So in this case, we are in the case of our smoothing, and the deterministic error, which is the bias, is very important. Okay. So in dark is the curve of the estimators, and the points are the observation. So the bandwidth h, we have to choose it not so small and not so big, to avoid the two extreme cases, the case of where the curve is very irregular and the case where the curve, where the bias is very, very important. So we have to how to choose h, what are the criteria to choose this bandwidth h. So I will focus on this model where while I equals to f of xi plus epsilon and xi are equidistant on the interval 0, 1. So the best h will be intuitively the h that minimize some error. The error in estimation, that means that some risk done, some error when we estimate f, the true regression function f, by fn at. So which the risk are? There's a lot of possible definition. For example, the maze is defined by the average of the expectation of the difference between f and the estimators to the power 2. So it's the average of the mean square error. The aids is its expectation is the maze. So this is deterministic and this is random. U is some known function. We put it in order to avoid the effect of the kernel K. Now the maze, we can calculate this. So as we know that the mean square error, this quantity, it can be written as the variance of the estimators plus the bias to the power 2. So we can calculate explicitly the maze. So it's proved that the maze, I am in the case where the observation are independent. So in this case, the maze is equals to this principal term plus other terms that we can control very well, but this is the main term. So the main terms, it's equals to h to the power 4 times some constant plus another terms 1 over n h times some constant. So this term at order h to the power 4, it's due to the bias to the power 2. And we have the order 4 because we suppose that f is twice regular. If we suppose that f is more regular, we will get better speed here. And this term, the term is due to the variance. So it's equals up to some constant 1 over nh. So for this reason, when h is very small, the variance becomes very big. So it's easy to choose the best h in the sense that it minimizes the maze or it minimizes the principal terms of the maze. It's the h that we have, the bias to the power 2 is almost equals to the variance. So if we call Hn star the minimum or minimizers of the maze, so an explicit calculation, so gives the expression of these minimizers of the maze. So it's equal to number of observation at this power times some constant. So we have its expression, but we can't use it in practice. Why we can't use it in practice? Because this bandwidth depends on some unknown parameters. And in practice, we must, to calculate our estimator, all the quantity must be known. So here it depends on sigma square. Sigma square is the variance of error. The error is unknown and its variance is also unknown. It depends also on the second derivative of f. So f is unknown and there is no reason that the second derivative is known. So the negative point with this criteria is that the minimizers is unknown. So now if we take the eights, so the eights, we will have the same problem. If we H and at will be the minimizers of the eights. The eights is unknown because we minimize something that depends on f and f is unknown. So we have to change the criteria. So the idea to change the criteria is instead of using f of xi, we will use some quantity that we observe and that is near f of xi. And thanks to our model, the quantity that we observe and that is near f of xi, it's the real input, the real output associated to xi, which is while I. So the idea is to replace f of xi but by while I. So we get the following criteria. So it measures the error from, this is the true output, and this is the predicted output according to the estimator f at. But we have a problem with this quantity. The problem that is that we are in the case that we call overfitting case, because we use the data twice. We use the data once to calculate the estimators, and we use the same data to calculate the risk. So we are in the case of overfitting. So we have to change this criteria, to change it in the sense that the data used to calculate the estimators must be different from the data used to calculate the risk. So I recall what is the cross-validation criteria, which is based on this idea to split the data on two blocks, one to calculate the estimators and the other data to calculate the risk. So the cross-validation criteria is defined by this average of while I minus the estimator minus I at the input xi. So what's the estimator? This estimator is obtained using all the observation, but we omit xi while I. And we can prove that this cross-validation criteria, it's equals to this quantity. That means we replace it f at minus I by the estimators, divided by some quantity that depends on the weights of the estimator, because we said that the estimator is linear and it's weighted, and this is LIXI is the values of this weight. So it's more useful to use the cross-validation as given in the lemma than in the definition, because here we have to calculate n estimators when I equals 1, 2, and so on. And here we have to calculate only the estimators f at, and we divided it by this quantity. So this cross-validation criteria was generalized in the sense that instead of taking one quantity, LIXI, we take the average of all those weights. So we get the following definition of generalized cross-validation criteria. So here, instead of taking LIXI, we take the mean. So we have this. And this criteria was generalized also to what we call Mallows criteria, using the fact that this decomposition near zero, 1 minus x to the power minus 2, it's equals near 0 to 1 plus 2x. So we get the following criteria called Mallows criteria. So finally, we defined three criteria. And each criteria to choose the bandwidth h, we minimize each criteria. So we will have, for these three criteria, we have three minimizers. So I recall that for those minimizers, we have its expression mathematically. We know that it decreases to 0 up to some rate. But its problem is that it's not observed. It depends on some unknown parameters linked to the error and to the function, unknown function f. So this quantity, it's the same problem. It depends on data, but it depends also on the unknown function, regression function. And this is Mallows criteria, which is in its definition is the error between the error of prediction, and here it's the error of estimation. So for IID observation, it's proved that all those bandwidths are equivalent in probability, and also this subject was studied in the 88 by several others. I give here a reference. So the purpose of my topic is to study the problem of the choice of the bandwidth h for in non-parametric regression, and when the error are dependent. So why we are interested by dependent error? I will give an examples where dependent error are very useful in practice. So here are real data from French pollution data. So we have several stations, and to each station we look at several times to some factors. To some factors that to some pollutant. So there are 4 pollutants, and the purpose is to explain the quality of R. So at station, we fix the station X. So we fix the location, and we look at several times for those 4 pollutants and the quality of air. So we have dependence in time, and also it's possible to look from station to another station and so on. So we will have dependence also on location, on space. So this is a space temporal dependence. And we have to study it in order to understand the quality of air, and also to do prediction for other time, for next time and next and other station, how much will be the quality of air. Now, there's a lot of model to describe the dependence of the observation, and to each model, it has its own calculation and technical calculations. So I give 2 blocks of models: discrete time dependent data and continuous time. Discrete time dependent data, for example, the autoregressive process. Autoregressive process said that the variables epsilon n, it depends on the observation from epsilon n minus 1 until epsilon n minus p plus some error. Also Arch process, it's the Arch process and so on. In the continuous time, so there's, for example, the Wiener process, Einstein and Blake process. They can be used, for example, to modelize the following problem. If we give G of t, the concentration of something in the blood, and we look at this concentration at several times. So we can modelize the error using Wiener process, for example, or Einstein and Blake process. This was the subject of thesis of our PhD student Jihad Belmadani, defended last year. Yes. Now to describe and to measure the dependence of the observation, we can describe them by, for example, the martingale difference sequences. That it includes the class of Arch process. I recall that a sequence is said to be martingale differences if it's measurable according to some sigma fields, and its expectation, the expectation of epsilon I known fi minus 1 equals to 0 almost surely. Another manner to describe the dependence of the observation is association, that said that the variables evolve in the same sense. They increase all together or they decrease all together. Another way, Markov chain. Also, there's also a lot of the class of mixing, and there's a lot of notion of mixing, like strongly mixing, beta mixing, phi mixing, and so on. So the idea behind is the following. We said that the coefficient, the sequence, the observation are mixings if the coefficient of dependence tends to 0 whenever the gap between the future and the observation become very, very big. So now I come back to our purpose. So the purpose is to define criteria to choose the bandwidth H in non-parametric regression, kernel regression model, and in the dependent set. So the first, I recall that the H, it was the error when we, between the estimators and the quantity to estimate. So Hn is the minimizers of its expectation. So Hn at is the minimizers of this average. So now we have seen that this quantity is not good because it gives an overfit. We are in the overfitting case. So if we add, in the independent case, it was some quantity that we added, but in the dependent case, the quantity will depend on R. The matrix R is the correlation matrix of the error, because the vector error here is dependent, and we call HM at the minimizers of this Mallows criteria. And next, I recall the last criteria, which is generalized cross-validation using the correlation matrix of the error. So we have 4 criteria if we take the expectation of the Tn, and 4 windows. So I recall that this window we can calculate it, since in fact the expectation is well evaluated. So this windows is not observable, and those this windows uses the criteria uses the gap between the estimator and the quantity to estimate, and for the 2 last quantity in green and in red, the criteria is based on the error in prediction, the gap between the true output and the predicted output. Our purpose is to control all those bandwidths. So we will suppose that our error are dependent in the sense of martingale difference conditions. I recall that means that according to some filtration Fi, the expectation of epsilon I known Fi minus 1 equals to 0 almost surely. And we suppose the moment condition on this stationary martingale difference sequences. So under this condition that we call the assumption A, all those 4 windows are equivalent in probability. So this is the first result. Now the second result, we are interested by the gap between 2 windows. So we do this. We have to add another conditions on the covariance of the error. So we suppose that the error is always martingale difference sequences, but we suppose that it satisfies the following covariance inequalities written here in blue. So that means that the covariance, that means that the covariance of the block of past of k epsilon and the block of other of the future of the observation is controlled by some function phi. It depends only between the gap between the future and past of the observation, and the function phi decreases to 0 at some rate, decreases to 0 such a way that the sum of s to the power 4 phi to s is finite. So for martingale difference sequences satisfying the moment condition and this covariance condition, we have the following result. We have that the bandwidth, here the minimizer of the eights, here the minimizers of the Mallows criteria in the dependent setting, and here the aids and the generalized cross-validation up to some rate, converge in distribution to central normal law, and we have its explicit variance. Now the rate, this rate 3 divided by 10, it depends on the regularity of the unknown function, regression function f. We have supposed that the function f is twice derivative. So if we suppose that it's it has more other derivatives, so the rate will be different. Now our other purpose is to control the excess, what we call the excess of error. So we recall that if the error in estimation, estimation, the gap between the estimators and f. So we look at this error when we take hm at, which is the minimizers of the eights, and when we take hm at, which is the minimizers of Mallows criterion in the case of dependent. And the same thing when we we use the generalized cross-validation criteria. So we have we look at the error for different values of h. So also the gap tends to 0, more precisely up to speed at to rate n times those gaps times converge in distribution to chi-squared of 1 degree of freedom times some constant c, and we have the expression of this this constant c. Okay, is this okay? Now, the purpose is to apply those results to the case when the observations, in particular case of martingale difference sequences, we will focus on the case of stochastic volatility process. So stochastic volatility process is defined by epsilon I equals to sigma I times Zi. Sigma I is we call it the volatility sequence. It's positive and strictly stationary. Zi is a sequence of IID random variables. It's called the noise. And sigma I and Zi are both independent. So the dependence structure of epsilon I is described by the dependence structure of the volatility sequence sigma I. I recall that to apply the previous results, we have to check 3 things: that epsilon I is martingale differences, a condition on a moment condition on epsilon, and the third condition concerns the covariance between 2 blocks of epsilon. So we prove that if sigma I is martingale differences, epsilon I is still martingale differences, and if the volatility sequence decreases the covariance of in the sense of the condition 3 decreases to 0 at the same speed, which is the sum s to the power 4. This function phi tilde is finite, and if we have the moment condition on the volatility sequence and on the noise are satisfied, then all the previous results hold true. Now I will give more explicit examples of stochastic volatility model. The first one is arch process. So for arch process, the stochastic volatility is the sigma I. It depends on epsilon I. So this is the stochastic volatility sequences. It's martingale differences. And if we take alpha in the definition, alpha must be less than 1. But to get the central limit theorem, we have to get another conditions on alpha. So we suppose that alpha is small such that this condition is satisfied. This condition allows to get the finite moment that we need. So if this condition is satisfied for this strictly stationary arch process, the conclusion of the previous result hold. Now I will give another example, which is a log normal stochastic volatility model. I recall what is log normal stochastic volatility. So the stochastic volatility sequence sigma I is defined as the exponential of an autoregressive process with noise. Eta is the noise of this autoregressive process. Gamma is supposed that to be less than 1 in absolute values, and eta is IID sequences of centered normal loop. We suppose that the noise Z is also follow also a Gaussian law. So if so, epsilon I recall is sigma I times Zi. So the sequence epsilon I is stationary martingale difference sequences. It's strongly mixing. and its coefficient of strong limits tends to 0 at this rate. And also it has finite, all integer movement are finite. So the previous result hold. So I recall that thanks to the strongly mixing properties with this rate, the covariance condition that we need on sigma I is, we prove that it's satisfied. Now another model is a gamma stochastic volatility model. So in this case, the stochastic volatility sequence sigma I is defined as the square root of a positive strictly stationary Markov chain, Hi. The marginal distribution of Hi is supposed to be gamma distribution, and also we suppose that the Markov chain is geometrically ergodic in the sense that the distribution of the Markov chain, the distribution at time n, knowing the distribution, knowing the values at time 0, tends to the stationary measure exponentially fast. So this condition, why we need that the Markov chain is geometrically ergodic in order to get the beta mixing properties for this Markov chain. And also we'll have its coefficient of beta mixing tends to 0 exponentially fast. Now, is it possible to get an examples of Markov chain that satisfies the 2 points? It's stationary, and it's a stationary measure. It's the gamma distribution, and it's geometrically ergodic. So the answer is yes. So this is an example. So this is the gamma autoregressive process. It's defined by this induction relation. This is the definition of autoregressive process of order 1. Rho is positive less than 1. The initial distribution is gamma, and the noise Xn is IID, is a sequence of IID random variables with a suitable distribution, which has this characteristic function. It's proven by Taylor in 94 that this process is a stationary Markov chain with gamma marginal distribution. And also it's geometrically ergodic in the above sense, and its coefficient beta tends to 0 exponentially fast. So for all those models, the previous result applies. So if we take a non-parametric model with the error is satisfied by one of those examples, all the results on the bandwidth hold. Yes, that's what I see. This is the result for gamma stochastic volatility models. Now I'd like to speak about the proofs of the results. So to prove those results, we need 3 blocks of tools. The first block concerns moment inequalities. The second block concerns maximal inequalities. And the third block concerns central limit theorem for quadratic form. So I will explain the grid lines for moment inequalities, more precisely what we call Marcinkiewicz-Zygmunt inequalities. So the first, this inequality stated in this theorem is due to the Burkholder in 88. It says that if we have martingale difference sequences with finite moment, with the moment that we need, then the moment of order p to the power 2 of this sum is controlled by n. It has the order n. It's not trivial order, but it's the optimum. We can do better than this for martingale difference sequences. This inequality is known as Marcinkiewicz-Zygmunt inequality. Now we use these inequalities, but for weighted sum of martingale difference sequences. So this result is an immediate consequence of Burkholder inequalities. So this weighted sum is controlled by the sum of the weights to the power 2, because if martingale difference times some constant is still martingale difference sequences. The other tool that we need is Marcinkiewicz-Zygmunt inequalities, but for quadratic form of martingale differences. That means we have here the sum until n, the sum of g until I minus 1, sum weights times the product eta I eta g. So this controlled by the double sum of the weights to the power 2. This is also, we use, to get this, we use Birkholder inequalities and some easy calculations. We use, and like Holder inequalities and so on. Now the other block of techniques that we need to prove the results are what we call maximal inequalities. So the maximal inequalities said that how to control the supremum over some set of the absolute values of a weighted sum. So what are the conditions on the weights for which that the supremum in the norm P of the supremum tends to 0 when the number of observation is very large. So this is true for martingale difference sequences, and if we can control we can control suitably those weighted quantity CIN. Also, we need the same kinds of tools, but for quadratic form, weighted quadratic form of martingale differences. So the supremum of the absolute values of this double sum of the product, what are the conditions on the weights that give us that this quantity tends to 0. Now to prove, I'd like to speak about the proof of the maximal inequalities. The proof is based on a beautiful argument called the chaining argument. It's used in the theory of empirical process to control the continuity stochastic properties for an empirical process. It's based on the following techniques. So I recall that we have to control the supremum over H that belongs to some compact set of this sequence of process. So to do this, the grid lines are the following. First, we give a covering countable subsets of H. So we cover the compact H by countable sets AK. So this first line is trivial. So to each H, there exists unique HK in IK. Unit. There exists HK very near to H, and that belongs to the covering countable set IK. So here we control the first term. Since we can control the covering set, we suppose that the covering set, it's we can control its diameters. It's say ρ k. So we get the supremum over this ball. Plus this quantity, which is the values of the process at HK, which belongs to the covering set. So now we will do what we call chaining. That means that to its covering set AK, we will define a thinner covering set AK minus 1, and AK minus 1, we will define another covering set AK minus 2 until AM, where M is fixed, and we will choose it according to our purpose. So we get the following inequalities. So from HK we get to the process at values HM. So here it's in the recovering set IM, and here it's the recovering set AK. So we get the last inequalities. And what's the good thing in the last inequality is that we get from the maximum, from the supremum, we get to the maximum. So this is a good thing because we can control the maximum. And here is the maximum only on one set. It's not, that means that only on HL. It's not on the product HL and HL minus 1. Why? Because this term is constructed using HL, because we have the chaining said that we can construct by induction. To each covering set, you construct another thinner covering set, and so on. And next, we will choose M and K according to our purpose. This is the grid lines of these very, very useful tools use it to study the stochastic equicontinuity of processes. Now I said that there is 3 blocks of tools. So the third block of tools concerns central limit theorem for quadratic form. So our calculation, although the problem is that says that the problem is that to prove a central limit theorem for the sum of the quantity in blue. The quantity is blue is epsilon I, the error. Sorry, is the error epsilon I times some weight plus the sum of the product, and we will take the sum of this, and the purpose is to prove a central limit theorem of this weighted sum of quadratic form of martingale difference sequences. So the first thing to do when we have to prove a central limit theorem for weighted sums is to evaluate the variance of the sum, because the variance of the sum will give the rate. This is Sn is the square root of the variance. So the first result that we have to study, to show, is to evaluate the variance of this sum. The variance of this sum, so we can calculate it. We will have the variance of we can calculate explicitly this quantity, and we prove that if we evaluate the covariance between 2 blocks, the product of 2 variables here and product here, and we can suitably control the gap between the past and the future of the observation, then the variance of this sum, it has the following order. So it's the exact order up to, this is the term is, it's not the main term. So the main term is the hn to the power 2 times constant plus 1 over n squared, the bandwidth to the power 3 times some constant. So we have the order of the variance, and next we have to prove the central limit theorem. So we prove that if the covariance decreases more to 0 according to we have seen this covariance inequality, we needed it only for the proof of the central limit theorem. So if we have these covariance inequalities, then the sum that we need of the quadratic form up to rate 7 divided by 10 converges in distribution to the normal law, centered normal law, and we have the variance of this normal law. We have the exact expression of this variance. So the proofs are based on those moment inequalities, maximal inequalities, and central limit theorem. For the dependent case that we choose, which is martingale difference sequences. Now we can do a lot of simulation to illustrate the convergence to the normal law, or the convergence of the excess of error to the chi-squared distribution. Here I will focus on 2 types of simulation. If you are interested in the paper that I mentioned, there's other simulations. So here is a simulation that concern the regression when the error is modelized by log normal stochastic volatility sequences. So we have seen that it depends on the parameters, 2 parameters, tau and gamma. So we worked with simulated data. So we will fix the function f. So the function f, it has this form, and so we have we plot the observations and the true function f. And here are some illustration of the convergence in the normal law of in the case of stochastic volatility error. And we studied here is the behaviors of the gap between the bandwidth using Mallows criteria and the bandwidth here Hn at is the bandwidth using the AIDS criteria. So for different values of gamma and different values of n, and this illustrated the central limit theorem. So here the result is not so good because we have seen that gamma must be strictly less than 1. And in simulation, gamma with these values is almost is very, very near to 1. And if we, but for very larger n, we get more satisfactory results. I think that I will stop here. Thank you very much for your attention. The questions, comments are very welcome. Thank you.
Thank you, Sana, for this nice talk. So all questions are welcome now.
I have a question, Wissam.
For that?
Sana, you say that this talk is related to machine learning.
Yes.
But I don't see what is the model of the machine learning approximation. For example, if you use a neural network where the shape of the neural network is taken into account in your estimation.
Yes, in machine learning, and more precisely in supervised learning. In supervised learning, the data are the form input-output. And we are interested by describe the link between the input and the output.
Okay.
And if we take the relationship, and when we speak about regression, when the outputs are continuous, takes continuous values. If they are discrete values, this is another problem. This is a problem of classification. So this is the non-parametric statistics. Its purpose is to estimate this relationship. And in machine learning, they are interested by the same problems, but mainly to do prediction with prediction error.
Mm-hmm. Okay, I see. Then okay, then your estimation give idea of how we can approximate this.
Exactly.
Okay, but not. Yes, I understand it differently. I thought that you have estimation about some models of machine learning methods. Okay. Okay, and I understand your answer was clear.
Thank you.
Okay. Are there any other questions, please?
Yes, please, Wissam. I have some not precise questions, but first I want to thank you, Sana, for her nice talk. Why you choose every time P more than 8? Why 8? Why not 9, 10? Why 8? Why?
Yes, it's good questions, and
thank you, sir.
I think it's a lot about this because I try to ameliorate this, but because in this we have to prove a central limit theorem for quadratic form. Quadratic form, that means that the product of two variables. Yes.
Okay.
So when we calculate the variance, we will have at least 4.
Okay.
Okay. And when we have, and you, in the case of independent random variables, do you remember to prove the central limit theorem? There's conditions called Lindeberg conditions. And in the dependent case, one method to control the Lindeberg conditions is to use higher moment of the sum. And the higher moment of the sum is the moment that we can evaluate well is the moment of order 4. So we have the moment of order 4 of quadratic form, so we get 8.
Oh, okay.
But I agree with you. If we have, if we don't use the moment of order 4, we use the moment of order, for example, the 2 plus something. it's possible. We will get. It's possible to get best result, but it's very, very, very technical. It's hard. It's technically hard.
Yes, I see. Another question: when you speak about ASE,
Yes.
How we choose the function your function How we...
It's also good questions. The question U is used according to the kernel K, because the kernel K that we work with is the kernel that is compactly supported. Compactly supported, that means that it's regular and compactly supported. So we will have some problem around, for example, suppose that it's compactly supported over the set -1 + 1. So around -1 and +1, there will be a lot of technical problem. So
okay.
to avoid this, we will multiply, but some function U. This function U, it's equals to 0 around when we have problems on the boundaries of this kernel.
Okay, I have another good question also. When you speak about H star n, the optimal H star n, you thought that we cannot use it because we have not the value of sigma square and other parameter.
Yes.
Can I change sigma square by another estimate of sigma square, and we use H star n or
yes, it's that we call the substitution, la méthode de substitution, or plugin method. Yes, it's possible to do this, but I'm not sure that it guarantees good prediction results.
Okay. But not sure. You are not sure that.
Yes. There's a discussion. Or no, there's a negative point with this method, but I think in connection with the prediction.
Okay. Now a question about eta I or eta j. Can you go to the slide where you speak about eta I equals to exponential something, please? Is in this section application to SVM process.
Here?
Yes. Sigma I, just a technical question. Sigma I equals exponential summation eta I minus g, and the index of eta must be positive, no? So the summation is from 0 to I, no? Sigma I.
Sigma I. Yes, I see. Yes, it's in Z rather than N.
In Z, okay.
Yes. Thank you.
Okay. And you, what do you mean by xi around x? Xi around x?
Yes, xi or yes. So the theoretical quantity, which is f is the regression function, and the regression function is defined by the expectation of y, known x, capital X equals to small x. Is it okay? Yeah.
Yes.
So how to estimate this? To estimate this, so what does mean while conditional to x equals to x? So we will, instead of x, we will look to the observation xi.
Okay.
And the observation xi are never equals to x. It happens with probability 0.
Okay, yes.
So we will suppose that xi are near x. So this and the questions is how to quantify the notion near. So
okay.
if they are in a neighborhood of x, for this reason we define h. So we can take an interval with length h or a ball if we are in a higher dimension, and we look at the observation xi, which in a small ball centered on x.
Okay. Okay. Thank you very much, Sana.
Thank you, Rafiq.
Okay, thank you, Rafiq. Are there any other questions, please? Okay, I guess that Rafiq asked all the interesting questions. So thank you, Sana, again. We're very glad to listen to you today.
Thank you very much, Sana.
Thank you, Sinadi. Thank you, Sam. Thank you, Rafiq.
Okay. Thank you. استنى Sana.
D'accord.
Okay, see you next week for another conference. It's about modelization for water treatment. It's dynamical systems, and the speaker will speak about a network with Tunisian, Algerian, and French researchers. And the name of this network is treasure. Treasure because the water is treasure, and treasure is the acronym of what? Of water treatment for reuse, okay? Or how to treat water to be able to reuse it for agriculture, for example. Okay, see you next week, I hope. Thank you very much.
Thank you.
Thank you.
Bye-bye.
Bye. ذكرت الفيديو